And he will talk about the interpretation debate and quantum gravity. Well, thanks for still being here. I suppose you're tired. I'm tired. So I'm going to talk about the interpretation debate and quantum gravity. So related to the role of the quantum, there is this other big hot topic in the foundation of physics, which is quantum gravity. And the question is whether there were influences or connection points during the history of physics between the interpretation debate and quantum gravity. And the answer is yes. That's what the article is about. It's not so much that the quantum gravity had a big influence on how the interpretation debate went, perhaps, but the interpretation debate definitely had some influence on quantum gravity. If you may say it like this, and how exactly this direction went, this is what I'm going to talk about. Ask you to talk a little loud. I try. I hear myself very loudly already, so okay. So in any case, it turned out that the interpretation debate is a very interesting angle to look at the history of quantum gravity. And before I begin, more probably I should say that the Handbook article on this topic has been written jointly with Alexander Bloom on this topic here, and the division of work that we did was that I did the part of Leon Rosenfeld, which is more or less the part of the prehistory on quantum gravity, and Alex covered the part between the 50s and 80s where we stopped, where things got a bit more complicated also. And I try in this talk to cover also Alex's part as good as possible. So there were the influences and connecting points were happened in several ways. And as I go on with my talk, I will try to draw a diagrammatic scheme on this slide that extends as I go on. So the first case that I would like to talk about is the one where commitment to a certain interpretation, well, the Copenhagen interpretation, led to a disapproval of the pursuit of quantum gravity. And that's the case of Leon Rosenfeld, as you might suppose already. That's him. Leon Rosenfeld is actually a very curious case because he was actually the first person to attempt the formal quantization of the gravitational field in 1913. But very soon after, he was actually very critical of this. So in a set of lecture notes that he gave a year year after, and they were published 2 years after his quantization attempt of the gravitational field. He wrote the following lines. The first successes of the theory of quantization of the radiation field made it possible to suppose for a moment that within the framework of quantum mechanics, this method provided a rigorous mathematical expression of the correspondence principle. But in reality, further approximation leads immediately to meaningless results, so that the new formalism can only be conceived of as a symbolic computational procedure. And he continues. There is no reason to think that the same method is likely to provide us with an adequate description of the interactions between material particles, or to express the same idea in other terms, that the concept of the photon can be legitimately applied to the analysis of fields other than pure radiation fields. So the way I read this quote is that he dismisses this usage of the quantization method that was successful for the quantization of the radiation field to the gravitational field as a purely formal thing, which has no empirical grounding. So the question now is, why did he change his mind? First of all, okay, his quantization attempt did not fully work out. So he might need was seeking for an explanation why this didn't work out. But there was also another thing that happened. For in the next year, in 1931, he began working with Niels Bohr in Copenhagen, and they worked very closely together on a response to Landau and Peier's critique to the measurement, the field measurement of the electromagnetic field. And so what I suppose is that while they were working together, Niels Bohr, Leon Rosenfeld was able to learn from Niels Bohr a new reading of quantum mechanics, which is more grounded in the appreciation of the empirical and physical, if you want. So on this, based on this new reading, he re-evaluated his previous attempt to quantize the gravitational field and dismissed it as purely formal. So this is an attitude that he would basically keep for the rest of his life towards the quantization of the gravitational field, though he later on added another argument against the quantization of the gravitational field, which is also grounded in the Copenhagen interpretation, and goes like this. So basically the argument is the necessity of a classical observer. So on the one hand, there is the system that is to be investigated. On the other hand, there is the external conditions which determine this investigation. And this specification of the two things, according to Rosenfeld, they need to be expressed in classical terms. And so he said that the metrical tensor appears as such a C number or classical number specification of conditions of observation, and there is no logical imperfection in regarding as fundamental the classical unquantized form of the equations expressing the connection of the metrical or gravitational field with the other fields. So basically implying that it's no logical imperfection, and probably even more reasonable to attempt semi-classical approach to quantization of gravity, or to bring the quantum together with gravity. So these two arguments that Rosenfeld kind of seemed to have derived from his reading of the Copenhagen interpretation against quantum gravity. And it seems to have been really great personal reading because another protagonist who is also grounded in the Copenhagen interpretation did have no difficulties to assuming that quantum gravity is something that needs to be pursued. And this is John Wheeler. This is him. So he arrived at the conviction that quantum gravity is something you should do by his method that he called daring conservatism. And that's basically, instead of trying to come up with creative ideas to conceptualize all the new fields and particles that were being discovered at that time, instead of doing that to, well, that's where this name comes from, daring conservatism, to use the theories that you have already at hand and push them as far as you can, and in this case bring the one theory of the quantum and the theory of relativistic gravitation together. So in his case, he kind of started with quantum gravity, but very soon after, he found that it's actually quite useful to not use Copenhagen interpretation for it, but instead an interpretation that a student of his came forward with, and that we've also heard of today already, namely Everett's interpretation. So that's what he said about Everett's in a published commentary to Everett's PhD thesis, in which he put forward his interpretation. So Everett's concept of a universal wave function provided the only self-consistent system of ideas to explain what one shall mean by quantizing a closed system like the universe of general relativity. So you can see already that Everett's universal wave function suited his needs more to to quantize the whole universe. And as you can see here already, he pictured the whole universe to be a closed system, in the sense that there would be no space left for an outside observer, and no classical observer in particular, to do the measurement. So it's difficult to apply the Copenhagen interpretation, or to make use of it here. And it seemed, or the hope, Wheeler's hope, was that Everett's self-consistent set of ideas would be a resolution here. So he tried to sell Everett's interpretation to Copenhagen, and however they didn't buy it, not for the reason that it was not a good idea, but they said it's an insufficient concept and that it lacks of meaningful content. And eventually Wheeler indeed let go of Everett's interpretation for his quantum gravity attempts. And so in something that Alex actually called a uniquely Wheelerian twist, he came back to the Copenhagen interpretation and made kind of like reinterpreted the Copenhagen interpretation for his needs, and this is how he did it. So this thing is a bit in the way, but what it says is beyond the rules of quantum mechanics for calculating answers from Hamiltonian stands the quantum principle. What he means by quantum principle is nothing than the Copenhagen interpretation that he elevated to a principle. And now comes the new part. It tells what a question it makes sense for the observer to ask. It promotes the observer to participator. It joins participator with a system in a wholeness, quite far into classical physics. we have to cross out that old word observer and replace it by the new word participator. And in this way, he kind of circumvented the outside observer and put it in the system somehow. So, yeah, trying to use the Copenhagen interpretation after all. In any case, while Wheeler was abandoning Everett's interpretation, there was actually someone else who started to make use of Everett's interpretation pretty much at the same time, and this was Royce DeWitt. This is also a bit curious, the case, because initially when Everett came out with his ideas, he found it very intriguing but didn't think it would have any effect on the physics. And it's, I believe it's still debated on what made DeWitt change his mind. I think it's Thiago Hartz who supposes that it's actually that Rosenfeld drove him away from using Copenhagen interpretation, because based on the measurement analysis Bohr and Rosenfeld did on the problems they were with the measurement of the electromagnetic field, DeWitt tried to use this analysis to conclude that it's necessary to quantize the gravitational field, and we can actually put this in this little diagram that DeWitt took apart, or like some sort of analysis that can be seen as part of the body of the Copenhagen interpretation, and derive from it the necessity of quantum gravity. And you can imagine from what I've said before about Rosenfeld that he did not approve of that, and he gave actually a very harsh critique. And Thiago supposes that this was what drove DeWitt away from this, and so he tried to do something else 10 years later. And he is actually very much along the lines of Wheeler, saying that if you want to quantize the whole system, there's no space for an outside observer. So this is what he says in a conference to anyone educated in the Copenhagen school. Such a function, and such a function is the wave function, the universal wave function, is meaningless since it leaves no room for a classical realm. The external observer has no place to stand. In order to give meaning to a universal wave function, one must find a radically new way of looking at quantum mechanics, and this is what Everett and Wheeler have done. However, for DeWitt, it was not necessary that the universe was closed. In the same year, 1967, he actually published a trilogy on quantum gravity, where the first part is on closed system, and where he made very elaborately use of Everett's interpretation. But part 2 and 3 are actually about the quantization of what we call infinite worlds, and there he did not mention any interpretorial issues whatsoever. Yeah, that's also one way to go, to just not talk about it. In any case, if you use new interpretations, then of course also new problems arise, and old problems get amplified, such as the question, what is the probability of the universal wave function? And new problems being the problem of time that is associated with the Wheeler-DeWitt equation. That's essentially static, or related to this is what if there's just one unique solution where you also don't have a non-trivial time resolution. I'm just skipping over this very quickly to make my, I guess, my final point that in the 80s there was actually a new twist to the debate on quantum gravity, where not the interpretations were just used for the sake of making sense of quantum gravity, but where perhaps also where new interpretations were used, but where also like problems that have existed in quantum mechanics, and more prominently the collapse of the wave function, were tried to make sense of by means of the workings of gravity. And that's what Penrose did, what we've heard already today, to hope that a theory of quantum gravity, or to say that the workings of gravity is actually why the wave function collapses. In a theory of quantum gravity, this would actually not be a problem anymore. So this closes the loop upwards, so to say. And I would like to conclude my talk by saying this is actually not the first time in history where people try to make use of gravity to make sense of problems in the interpretation of quantum mechanics. And this makes the whole loop back to Rosenfeld, because before he quantized the gravitational field with the methods of quantum field theory, he, quite a few years earlier, he was a postdoc with de Broglie. And as you know, de Broglie had difficulties accepting that the wave function is on configuration space. He would have preferred that the wave function is real. And Rosenfeld at that time, he constructed a wave equation or wave function on a 5-dimensional space, incorporating gravity. And de Broglie had hoped that this would help him for his needs to interpret the wave function as something real. Well, that's all I wanted to say. Thank you. We have some questions.
Okay. Yes. If in the well-algorithm interpretation there is no time, how can the wave function collapse without time?
This is a very excellent question, and it's not, I don't think I'm the one to answer it. Yeah. So, I'm just a historian.
Yes, okay. Thank you.
Thank you very much. That was a beautiful presentation. One question to what you said about this early 1932 Rosenfeld quote puzzled me a bit. For one thing, I mean, the work with Bohr was in defense of the possibility to quantize quantum electrodynamics. Why should that have made him critical of the idea of the photon being a very useful concept?
I think you asked me this question already, like at some point. So I don't think he was not critical of the quantization of the radiation field, because he believed that this has origins in empirical situations, that this is empirically necessary to have a quantized theory of the radiation field, whereas the wish to quantize the gravitational field, there's no empirical need, he didn't see any at least. And it's just taking the formalism and applying it to a new field.
But then Daly explicitly talks about the photon, right?
Yeah, right. Which so the photon is something that appears if you quantize the radiation field.
Yeah, but there he says it's useless outside of the free field. Right? So it seems like that's a very skeptical remark.
So I understand it. It's like to try to get something like this is. You shouldn't try it if you don't want to get this. Yeah. That's how I understand it.
But there's some remarkable because you see, we have occasion data between of Notre Dame, I will read the week. And we discussed the issue. I asked him about this equation, and he told me he doesn't believe in this equation. Because their problem is concerning Hamiltonian. And that's problem in the methodical question. Because Hamiltonian is equal to 0, but you have inside Hamiltonian 2 parts. But that's the kind of question of time, because you have 2 parts in the Hamiltonian, not only one. And this first quantum, the matrix first, that's a part of the normal you can use as a parameter. So you can resolve the equation in this way. That's to answer the question. But that's the
Yeah,
he doesn't want to believe in the equation.
like some sort of time variable, but yeah. Yes.
Yeah. I have a brief question concerning this relation between interpretation of quantum mechanics and the way people are thinking quantum gravity that you are discussing all during this talk. You mentioned the role of Rosenfeld, the role of Wheeler. Did you go also to modern physics, for example, about the role of Carlo Rovelli, for example, relational quantum mechanics, this kind of things? It's a very similar story, it seems.
No, we stopped in the 80s, or
Fuchs.
pretty much Alex stopped in the 80s, because then it seemed that the interrelation between quantum interpretation and quantum gravity got also more complex, and that's what we just didn't cover, weren't able to cover anymore. So we already had like 20-something pages. So.
Thank you.
Yeah. Any more questions? Yeah. Thank you. Now we have a talk by Marc Lechesray from this ABT Institute, and it seems to be in French.